All right, so what we have, it says a fisherman yanks a fish vertically out of the water with an acceleration of 2.5 meters per second squared using very light fishing line, has a breaking strength of 22 newtons. Right, now to give you an idea of 22 newtons, right? So 22 newtons, if you did 22 newtons, you divide it by 9.8 and multiply it by 2.2. It's only like 5-pound fishing line. So to give you an idea, 5-pound fishing line is really light, what's called light tackle, right? And so you have a light rod and you have light tackle and you're fishing for light fish, small fish, brim, crappie, small bass, maybe trout, right? Little guys. You're not looking about the big lunkers, right? I fished one time, the biggest fish I never caught was because I was using 10-pound line. The guy said, when you come to this place, make sure you have 20-pound line. And I was like, catch a fish that big. Well, I 10-pound line. I flipped it into the corner, hit the lily pad, pulled it off the lily pad. It was a huge 10.5-inch pumpkin spice lure, not the flavor, the color. And it fell out and bang, it hit it. And I, boom, pulled it up, line broke. He goes, you don't have 20-pound line, do you? I went, no. He said, there's a 10.5 pounder that lives in that corner. I said, how do you know? He says, I've caught it twice. And he turns it back in. He lives in that corner. I was like, about 10.5 pound bass. That'd have been awesome. The biggest I caught on the day was a 5-pounder. The 5-pounder is a nice fish, but boy, that 10 would have looked nice in a picture because I would have turned it loose, right? So when you're talking about this, a 5-pound, if you pull hard and something weighs 5 pounds, you're actually increasing the force, right? Because just the weight of the fish is 5 pounds. If you have a 5-pound line and then you pull, you're going to break the line. So that's what this is going to be. So what we have is we have two things that are happening in this particular thing. So you have the fishing rod and you have the fishing line, right? And if I have the fish, right? If I have the fish hanging like this, if he's just hanging there, right? If he's just hanging there, this is the mass of the fish times G, right? The force of gravity. So we would have the force of gravity on the fish if he was just hanging there. But if I were to then accelerate this, I'm going to accelerate this. It's going to be mass times acceleration, and that's going to be a force of acceleration. And these two things are what's acting here. So if you did this problem and you just took 22 newtons equals force times acceleration, or mass times acceleration, right? And you took m equals 22 newtons divided, and then you divided it by that 2.5, right? Then you got a mass. You forgot that the fish weighs something as well. Because if you're pulling a fish out of the water, you have to take into account the mass of the fish if you're holding it. It rods out, you're just holding it. And then when you accelerate it, that's a whole different thing. So these two things, the force of acceleration plus the force of gravity, add up to your 22 newtons. And then all of a sudden, because the mass is common to both, this is the mass times 2.5 plus the mass times 9.8. When I get my 22 newtons, then I'm going to get, what's that, 12.3. So 12.3 times the mass equals 22 newtons. Okay? So you end up with the mass being 22 divided by 12.3. And you end up with the mass as 1.79 kilograms. much smaller than if you don't take into account the weight of the fish. Yes, sir?
I know we should probably know this, but is when you converted from newtons to kilograms, how did you do that?
I just divided. There's 12.3, right? These are accelerations. This is a great point. This is the acceleration of 2.5. This is the acceleration from gravity. So really what I have, this 12.3 is the total acceleration of the object. And because force is mass times acceleration, if I take force and divide it by acceleration, I get mass. So that's what I did here. That make sense? That's a good point. This number is actually the acceleration, one from gravity and one from me. Yes? An elevator. Okay, consider an elevator. Let's just think. An elevator's got cables, right? And let's just assume it just has cables and the cables get rolled up. And let's make the cables not weigh anything. Because cables weigh a lot. But let's just make the cables not weigh anything. So you just step into the elevator. So when I step into the elevator, you have the weight of the elevator's box. You have me and whoever else gets on the elevator. And then, so they already have that much weight on them. Then they're going to accelerate. So those cables have to be able to handle the weight of the box, plus the people, plus the acceleration. That's why this elevator does not accelerate very fast. This elevator here is really slow. But it's only going one floor, and I don't have to have as big a motor if I accelerate slowly. So you see how the cables have to be able to withstand that. Okay? Yeah.
So in that situation, you'd have the force of the elevator and the force of the acceleration of the elevator and force of gravity in the elevator plus the people inside.
Right.
Their acceleration and gravity.
Correct. Or you could do the weight of the elevator with the people as one big force, and then the force of acceleration. See, all of a sudden, I've got an elevator, but really what I have is I have a fish being pulled out of the water problem. And I can be using an elevator, doing the same thing. So, the inertia of the object has to be taken into account. The inertia of the object, just the force of gravity, right, is associated here. Then you have the force of acceleration upon top of that.